Hello, I'm Vikram from Computer Science and I'm going to be solving question number 4 for our Endsem examination. So let's start. Alright, so this here is our fourth question. It asks us to solve the following non-homogeneous linear ODE by using either variation of parameters method or undetermined coefficients method. So I'm going to be using the variation of parameters method. So for variation of parameters method, we'll have to find out the Wronskian first, which is represented by W. For the Wronskian, first we'll have to find out the homogeneous solution for this non-homogeneous linear ODE. So for that, let's write the corresponding homogeneous equation first. Then we'll take a trial solution e to the power Rx. So y dash is equal to r e to the power Rx and y double dash is equal to r square e to the power Rx. So on substituting we get r square e to the power Rx plus 9 e to the power Rx is equal to 0, which is equal to r square plus 9 is equal to 0. And this is the characteristic equation, and I could have directly gotten that, come to that, but I felt like this would give a much better explanation of how it is obtained. So going further, we get r is equal to 0 plus minus 3 iota. So from the following values of r, we can get our y homogeneous as C1 e to the power 3 iota x plus C2 e to the power minus 3 iota x. Alright, and this can be further simplified as, okay, wait, before that, we know that Euler's theorem gives us the following formula, which is e to the power a iota x is equal to cos ax plus iota sine ax. Alright, now using this in that, we get y homogeneous is equal to C1 cos 3x plus iota sine 3x plus C2 cos minus 3x plus iota sine minus 3x. So on opening the bracket, when the minus the cos term doesn't change, as cos of minus theta is still cos theta, but cos of sine of minus sine theta is sine of minus theta is equal to minus sine theta. So that brings us to the following step, where we can further write this as C1 plus C2 cos 3x plus C1 minus C2 sine 3x iota. So C1 plus C2 and C1 minus C2 can be written as different constants C3 and C4. So on comparing it with this form, we can say that y1 is equal to cos 3x and y2 is equal to sine 3x. So since we found out y1 and y2, now we can find out the Wronskian. The formula for the Wronskian is w is equal to y1 y2 dash minus y2 y1 dash. So it can be represented by the following determinant. So moving further, so let's put in the values and find out the Wronskian. So this gives us cos 3x into 3 cos 3x minus sine 3x into minus sine 3 sine x. So minus minus cancel, we get taking the 3 common, we'll get 3 into cos square 3x plus sine square 3x, which gives us the Wronskian, which is equal to 2. Now, why were we exactly finding out the Wronskian? Well, to answer that, in the method of variation of parameters, we have been given a formula to find out y particular, which is given as minus y1 into the integral of y2 into r of x upon the Wronskian dx plus y2 into the integral of y1 into r of x upon the Wronskian dx. So let us call this term as u1 and this term as u2. Alright, so plugging in the values, we get t is equal to minus cos 3x. I'm gonna take out the Wronskian outside, which is 3, and this was sine 3x, and we know the r of x was cosec of x upon well, nothing right now because we took it out. Then y2 was sine 3x upon 3 again plus cos 3x cosec x dx. So just for simplicity, we're going to solve u1 and u2 separately. First we'll solve u1. This was u1. We're gonna leave the 3 over there because we don't really need to do anything extra since it's just a constant. So for u1, let's start off. This was u2, sorry. So u1 is equal to integral of sine 3x cosec x dx. So sine 3x is given as 3x is equal to 3 sine x minus 4 sine cube x. Alright, so u1 is equal to integration of 3 sine x minus 4 sine cube x, and we're gonna write cosec x as 1 upon sine x dx. So sine x get cancelled on top and below, so we're left with integration 3 minus 4 sine square x dx. Now this can be written as 3 into 1 minus 3 sine square x dx minus sine square x dx, which gives us 3 cos square x. I'm sorry, that dx wasn't really necessary. I just put an extra one over there. Yeah. So this gives us 3 cos square x minus sine square x dx. Now we're going to use two properties of sine 2x, which are cos 2x, which are cos 2x is equal to cos square x minus sine square x, and cos 2x is equal to 2 cos square x minus 1. Alright, so for that we'll have to split u1 as follows. So 2 cos square x dx plus cos square x minus sine square x dx. This is just the property box. So we can write 2 cos square x as cos 2x plus 1, which is how we're gonna write that right now. So u1 is equal to integral of cos 2x plus 1 dx plus cos 2x dx, which can further be written as 2 cos 2x dx plus integration of 1 dx. Now integration of cos 2 dx will be 1 upon 2 sine 2 dx, sine 2x plus x. So this leaves us with u1 is equal to sine x upon sine 2x plus x. So we have found out u1. Next we will go on to find u2. So let's start. For u2 is integral cos 3x sec x dx. Now cos 3x is written as 4 cos cube x minus 3 cos x. Let's just substitute that in. We are given 4 cos cube x minus 3 cos x upon sin x. I wrote cosec x as 1 upon sin x. Should be clear. Now this next step is pretty important. We'll substitute sin x with t. So sin x is equal to t. So the derivative of this, that is dt, will be given by dt is equal to cos x dx. So we'll take out cos x common from here. Let's not completely write it in terms of t right now, because there's a lot more that can be done. So one cos common, so that leaves us with cos square x minus 3 inside and a cos x outside upon sin x dx. So this gives us dt. This here is our t. Also we can convert this in terms of sine square t. So that can be written as 4 minus 4 sine square x minus 3 upon sine x cos x dx. Let's flip the page. So we were at 4 minus 4 sine square x minus 3 upon sin x into cos x dx. u2 is equal to 1 minus 4t square upon t dt, since t was sin x. So what else can we do now? Simple. We just simplify it. 1 upon t dt minus integration 4t dt. What can be this written as? 1 t minus 4t square by 2. So u2 is equal to 1 of sin x minus 2 sine square x. Alright, now we put in u1 and u2 into the formula of yp. Yp is equal to y1 u1 plus y2 u2, and the Wronskian was there too, since I didn't take Wronskian to be part of u1. So y1 was cos 3x upon 3 and u1 was sine, there is a minus sign over here in that formula, minus cos 3x to sine 2x plus x, if I'm not wrong. That's it. Plus we just found out u2, sine 3x upon 3 into natural log of sine x minus 2 sine square x. It seems about correct. So the final solution y, which is equal to y homogeneous plus y particular, comes out as c1y1 plus c2y2 minus y1 u1 upon the Wronskian plus y2 u2 upon the Wronskian, which can be written as y1 common c1 minus u1 on the Wronskian plus y2 into c2 plus u2 upon the Wronskian. It will give us cos 3x into c1 minus sine 2x plus x upon 3 plus sine 3x into c2 plus natural log of sine x minus 2 sine square x upon 3. It's a pretty long answer, but I think that should have done it. I'll just write it a bit more clearly in the next line. Y is equal to cos 3x c1 minus sine 2x plus x upon 3 plus sine 3x c2 plus natural log of sine x minus 2 sine square x upon 3. Hope that is a bit more visible. So that's the final answer. We could have solved for C2 and C1 if we had been given the initial values, but we haven't been given the initial values, so that's all I can do. Thank you for watching.